Morning, everyone. I've seen a couple of emails and also some chats about the respondus. I have contacted some other technologists in the Department of Biology to try to help us get that figured out. For those of you that have downloaded it before, it should still be there on your computer if you use the same computer to write this exam. But Melanie Smith, who's one of the technologists in the department that you may have run into before with some of your other courses, she's really good at figuring all this stuff out. So I have sent a message to her. She helped me do it for animal histology last semester. So I'm hoping that she'll be able to reply with some instructions that I will then post on D2L. I asked her to give me some text that I could simply copy and paste into the news part of D2L so that you can see from there. But if anybody else, I don't know if there was a new chat since I started saying that. Looks like there has been. If anybody else has figured out another way to do it, but in any event, I've asked for some help from the Department of Biology technologists to get that figured out. Because I go into D2L differently than you guys do, because I'm going in to set things up. I can't see. I can turn it on to see what you see, but I can't do a practice run of respondus lockdown, at least as far as I can tell. So hopefully I'll have some answers for you soon about that, obviously, because the test is on Thursday, so we need for that to be working. I'm just going to check the chat here and see. I can't find it anywhere on the Laurentian websites for the respondus. Okay. And IT hasn't replied either. Okay, so usually you have the option to download it when you open the test. Amy says, okay. So anyway, maybe that's the way it works. Yeah, so you have to open the test a few minutes early, maybe, or get onto D2L a few minutes early, and that's how you can do it. The test is set up to have respondus attached to it, so that you need respondus to do it. So that's probably okay. Also, Amy says it needs to be updated as well. Okay, so we're going to make sure we allow for that at the start of the test. But like I said, I'm waiting on some input from the technologists in the department who have had a lot more experience with getting respondus on there. So don't panic. I'll get that information and I'll get it on D2L. So please make sure you check D2L for that. Okay, so you can see that again today I'm teaching to you from room S511, which is the teaching lab for the course, because we're going to do a little bit more Blackboard stuff again today. Today we're talking about logistic population growth. Last time we talked about exponential. Today we're going to talk about logistics. So I'm going to jump right into the lecture and get started on that. Now, okay, let's see, here we go. Okay, so, when we talked about exponential growth last time, we assumed that per capita growth rate, that little r value, per capita growth rate was constant, right? That's the key assumption of the exponential growth model, that r is constant. Per capita rate of growth is constant. So that means that birth rates and death rates are constant, right? Because remember that little r, that per capita growth rate, it's the difference between births and deaths. So in that exponential growth, r is constant, which means that birth rates and death rates are constant. Now, as we sort of alluded to already last time, that's not realistic in a lot of situations. Maybe when a population first establishes and starts to grow, that's how it's going to be. But eventually, that population, all the individuals are going to be competing for a limited amount of resources. And so things are going to change. That growth rate, that little r value cannot stay the same forever. That's just not biologically real, right? So it's not realistic for many situations because the population can't grow indefinitely. So the environment's not constant. And so resources like food and space and mates, those are going to be limited things. So as populations grow, then we expect that competition, intra-specific competition, right? Intra means within the species. So individuals within that population are going to be competing with each other. And so that's going to cause some changes in birth rates and death rates, right? So there's going to be increases in death rates because maybe starvation or disease or predation rates, right? So so right away, if death rate changes, that means that value of little r is going to change. Right? There also could be decreases in birth rates. That value of little b could also change, right? Because if there's competition, maybe a female, for resources that are limited, maybe a female is not going to get enough to produce healthy offspring, right? And so she herself will be compromised, and then she can't produce kids, right? So there could be a decrease in birth rate. Also, when things get really crowded and there's a ton of competition, individuals might leave, right? So they might emigrate out of that population. And of course, that's going to also change the value of birth rates and death rates and little r. So what we then expect in a more biologically realistic situation is that as r decrease, that r is going to decrease as population size increases, right? So as the population gets bigger, that per capita growth rate is going to come down. Okay, it's not a constant value in the case, in most sort of realistic cases. And so logistic population growth then is a model of population growth that is, we call density dependent. So the per capita growth rate, that little r value, or if you remember, the other way to look at little r is this dn over n dt, right? That's what little r is. That per capita growth rate is going to decline. It's going to get lower as population size or density increases. So we have that dn over n dt on the y-axis, and we have population size on the x-axis. And so that population size, that's a measure of population density, right? A measure of population abundance. And so what happens is that r is going to get smaller as n gets bigger, okay? So this is a reflection of that intra-specific competition. And so to develop this model of logistic population growth, we assume that per capita growth rate will decrease in a linear fashion, which is why it's a straight line on this graphic, right? So it's a straight line, a decreasing line. So that per capita growth rate, that little r value, it's going to decrease linearly in this straight line pattern as population size gets bigger. And this is, again, what's shown on the graph now. We have a straight line with a decreasing slope. So the highest possible value for per capita growth rate is called RM, and that's noted here on the y-axis, this top value. So the M stands for maximum. So that's the maximum per capita growth rate possible, right? And this is determined by the reproductive abilities of the species. So it's going to differ depending on what species you're talking about. The RM value for like a grasshopper or a fruit fly that has a really fast reproductive rate, it's going to be a lot higher than for something like an elephant or a human that's going to have a lower RM value, right? Grasshoppers reproduce much faster than elephants, so their per capita growth rate is going to be a larger value. And when R is positive, that means the birth rates have to be higher than death rates, right? You know that. So remember that the R value is the difference between B and D, birth rates and death rates. So when R is positive, that means the birth rates have to be bigger than the death rates. So R is, remembering, right, that R is equal to B minus D. And so that means the population is going to increase in size. But when R is negative, so that means the death rates are bigger than the birth rates, right? So when R is negative, there's more death than birth, and the population is going to decrease in size. Right? So, and then the population is basically staying at the same size. That is, the growth is 0 when R is equal to 0, okay? So that's what it looks like. So on this part of the graphic up here, right, in this space, this is when birth rates are higher than death rates. And then in this space down here, this is when the death rates are bigger than the birth rates, right? And then we have this 0 value of R right here, and that's when there's a balance, right? The population is staying the same size. There's no population growth. R equals 0. Per capita growth rate is 0. Okay, so this is the same graphic, but now I've added some arrows because I want to talk about what's happening here. So on the graph, again, you can notice that per capita growth rate value, that little R value, it's a positive value at small population sizes, right? So the way the graph writes, so small populations over here on the left side of the x-axis, and then larger population sizes are over here on the right-hand side of this x-axis that represents population size, which is M. Okay, so in this space on the graph, right, the R value up on the y-axis here is a positive value. So at small population sizes, that R value is a positive value, right? But when you get to larger population sizes over here, now the R value is below 0, right? The R value is below 0, okay? So we have R as a positive value here when population sizes are small. Then we go out to bigger population sizes now, and then we have an R value that's negative, okay? And then the point at which R is 0, this value, right? This point at which R is 0, which is this green circle right here, this is an equilibrium point, Okay, this means that populations do not increase or decrease, right? We said R is 0 at that point. There's no population growth. Okay, so we call that an equilibrium point. And in the case of this logistic model, it's called a stable equilibrium point because if populations deviate away from that point, they have a tendency to come back to it. Okay, so if populations are really big, right, there's going to be all this competition and stuff, and so there's going to be a tendency for the value to go back towards that 0 value. If populations are really small, lots of resources, everybody's going to reproduce, and it's going to increase towards that value. So because populations that are different from that equilibrium value have a tendency to move back to it, we call it a stable equilibrium value, okay? And that's what's indicated by the arrows on the graph there. And so this equilibrium point, right, is when the population size is not increasing or decreasing. And in the logistic model, we call that the carrying capacity, which is indicated by capital K, okay? So that is the carrying capacity, which you know already is you've learned about it before, right? It's the maximum number of individuals that the resources in the environment can maintain over time, right? It's what that patch of habitat can supply to the population there, right? So the symbol we give to this idea of carrying capacity is capital K. Okay? Again, it's the maximum number of individuals that the resources in the environment can maintain over a length of time. Okay. So from that graph, and I've inserted the graph back here small in the corner of the slide so you can see it there. So from this graph, we can develop the equation for logistic growth, which is what is shown here. There's just two ways to show it. One is with 1, which is just the same as K over K, right? K over K is the same as 1. So there's just two different ways to write the exact same equation. I put them both here because you'll see it both ways when you read the literature about logistic population growth, but it means exactly the same thing. Hopefully you know that from simple math, right? K over K is 1. And so that's why it's shown like that there. Okay. And so when we look at this graphic again, here we have a straight line again, right? We've talked about this before. You know that the formula for a straight line is y equals mx plus b, right? Y is the y value, which is dn over n dt, right? M is the slope, right? So that's, in this case, remember, it's a negative slope. So we have negative Rm, right? We have negative R value for the slope because it's a decreasing slope. And it's divided by K. So if you remember the old way that you probably learned about how to calculate a slope a long time ago was that formula called rise over run, right? So we can use that. That's exactly what's indicated here by this negative Rm over K. The rise over the run, okay? So it's negative Rm divided by K. We're using the rise all the way up to Rm and the run all the way out to K, which is what gives us this Rm over K, and it's negative because it's a negative directional slope. Okay, so, and then X, right, is N value, that's the X value. And then if you remember, B is the intercept, and in this case, the intercept is Rm. It actually is Rm. So you can see how we can develop the equation using this y equals mx plus b to represent the pieces of that straight line on that graphic, right? And again, remembering that the old way we used to calculate slope was this rise over run. And so the rise is Rm and the run is out to K, but we put a negative value because it's a negative direction slope, right? So again, we can put it in the context of this y equals mx plus b. So we're going to do a bit of Blackboard stuff just to sort of show how this is developed into the logistic growth equation. Hopefully you'll be able to see everything I'm doing again. Okay. All right. So to first write it out in that y equals mx plus b formula, which you have right there on your screen, but I'm going to write that out again, and we're going to just sort of work through it, right? So we have the dn over n dt, right? So that's the y part. And then we said the slope is that minus negative Rm over K, right? That's the slope of the line. And we times that by the X value, right? X, and in this case, X is that population size. Again, this is what you have on on the slide, it's already there. I'm just writing it out for you again. And then plus the intercept, right, which is Rm, okay? So again, I'm just writing out what's on the slide there, but I want to show you sort of how we work it through to get to the equation for logistic growth. Okay, so we have that equation. So the first thing we need to do is to sort of simplify and rearrange the values that we have here to start with. So we'll do a little bit of simplifying and rearranging. So the first thing that I want to do is, because we have this negative sign here, the first thing I want to do is just switch around the values because of that negative, and also set it up so that we can eventually factor out the Rm. So the first thing I'm going to do is just rearrange this side of the equation to make that negative a little easier to deal with. Okay, so I'm just going to erase it and rewrite it here. Okay. So Rm minus Rm and over. Okay. Right. So again, I just basically switched it around so that we don't have a negative at the start of this side of the equation. Okay. So then the next thing to do is to factor out the Rm. So Rm is constant to both parts of that right-hand side of the equation, right? So we can factor out that Rm part. Okay, so I can do that. So Rm is now going to be factored out because both parts have that Rm, right? So it's going to be 1 minus n over n, right? I've simply just factored out that Rm value. Now, the other thing we want to do here is, right now, what's on the left-hand side of the equation, that's the little r value, right? That's that per capita growth rate. But if you look at the equation on your screen, it's dn over dt, it's population growth rate. If you remember, dn over dt means the change in population size with respect to time. So we want to get that to be on the left-hand side of the equation. And right now it's complicated because we don't have that on the left. We've got this extra n down here that we need to get rid of to take care to get to the population's growth rate on the left-hand side, rather than this value, which, if you remember, this is the same as little r, right? So what we need to do is multiply both sides of the equation by n to get rid of this n, right? If you remember that sort of simple math factoring there. So we're going to multiply both sides of the equation by n to get rid of the n that's here, okay? Hopefully you can still see it. I'm trying to watch my screen to make sure you can see what I'm writing. Okay, so then we're going to multiply both sides of the equation again so we can get it to population growth. So now, right, it's going to be dn over dt, because we multiplied this side by n, which gets rid of that n that was in the bottom part of the denominator. So now we've got Rm n times 1 minus n over n. So there's where the n shows up that we multiplied it into there, right? Okay. So now you can see that is what's on your screen, right? That's one of the equations that represents logistic population growth. So that's how we got it. We took that information from using the slope of the line of that equation, and we did a bit of simplification and solving, and we end up coming to that equation that represents population growth, okay? So if you remember when we talked about exponential growth as well, this first part of the equation, this dn over dt equals r times n, just that part, like, sort of ignore that n for a second. But just r times n, that's, if you remember, one of the equations that we use to talk about exponential growth, right? So it tells you a little bit about what's happening in this equation, right? It means that this piece of the equation over here, this 1 minus n over k, this must be the part of the equation that makes it a density-dependent response, right? Because this dn over dt, that's population growth rate, equal to r times n. You remember that r times n, that's how we explain exponential growth. So again, that means that this piece of the equation over here, this 1 minus n over k, This is the part of the equation that makes this logistic, that is, makes it density dependent. So I'm going to talk about that a little bit more in the next slide here. So I've actually circled that piece of the equation to show you this is the part that makes it density dependent. Okay, so in a really small population, so this graphic that's here now we have time on the x-axis and population size on the y-axis going up to k, which is that carrying capacity, right? So in a really small population, so I've got a little box over here, in a small population, it means that population size is much less than that carrying capacity, right? Whereas in a large population, you're going to be getting an n value that's much closer to that carrying capacity value. So we're going to have a look at that and have a look at how it relates to this density dependent part. Okay. So again, when you have a really small population, right, that means that the population size is going to be much smaller than the carrying capacity value, right? When the population is small, it's way below that carrying capacity value. So if we made this into an example with some numbers, just to kind of have a way to look at how it works out. So let's say that we have an n value, we have a population size that's just 1, like this is just obviously a very small population size. Okay? But let's say the carrying capacity for that population is 250. Okay. So if you think about that, that piece of the equation, of the density dependent equation, of the piece of the logistic equation that's density dependent, that 1 minus n over k, let's just look at that piece of the equation for a second. So if you look at that 1 minus n over k, if you have a population that's really small like this, right, that means that this value of n, it's only just, it's 1. And the k value, we're saying it's 250. If you do the calculation of 1 over 250, it's a really, really tiny number. So we're looking at 1 minus, it's like 0.00400. I don't know how many zeros here. 0.04. It's a tiny number. It's basically 0, right? So we're basically looking at 1 minus approximately 0. And 1 minus approximately 0 is 1, right? It's basically just 1. So if we go back to this piece of the density dependent equation, right, and we look at the equation, now we look at the logistic growth model, right? So we look at this Rm times n, right, is 1 minus n over k. If we look at that now and we sort of substitute in these values, we've just calculated that this value of 1 minus n over k, it's really just 1, right? We're looking at this value, it's basically just 1. So now we come to an equation that is this. Rmn times 1 is just the same as saying Rmn, right? And if you remember, I just reminded you that the equation for exponential growth is R times n. So we have, at these small population sizes, we have exponential growth happening. And if you look at the curve on the slide, it's exactly what you see. At the starting point over time, right? This is population size versus time. At the start, it starts exponentially because at really small population sizes, we're far away from that carrying capacity. And when you do just this sort of example calculation, you fill in the math, you end up with basically just R times N. So it makes sense, right? That's what shows us that it's exponential growth at the start of that population's existence, if you will. Okay? So again, we have the equivalent of exponential growth happening at small population size. Now, let's do this example again, but let's look at the opposite side, okay? Okay, so now, when we have the case when the population is getting close to the carrying capacity. So population is getting close to the carrying capacity. So we have a big population size, right? We have a large population. Now in this case, the N is going to be approximately equal to K, right? We're getting to this point where population size is so big, it's close to the carrying capacity, okay? So using our example we used before, let's now say, population size is 250 and carrying capacity is also 250, right? So similar to the example we did before, except that we had the small population size to start, okay? So now when we so what we're saying is that N and K are basically equal to each other, right? At these large population sizes. Okay, so if you now look at it in terms of the pieces of the equation again, right? So this means that N over K is basically the same, right, as K over K. It's the same thing, right? And so that means that when you take the piece of the equation that's about density dependence, right? That's that 1 minus N over K bit, right? Now you're going to have 1 minus 1, right? Because if they're the same value, that equals 0, right? So now you have 0 there. So if you put that back into this equation for logistic growth, right? Now you're going to have your Rn N is going to be times 0. We just said that this piece of the equation is now 0. So if you have something times 0, you end up with 0, i.e. you have 0 population growth. So this means that dN over dt is 0. And that's exactly what happens at carrying capacity. If you look at the graphic again, once we get up to K, population growth is 0, right? Anything times 0 is 0. So dN over dt, it becomes 0. Again, it's just a very simplistic approach to use these numbers just to show kind of how it works. But this is what you end up with, so that this piece of the equation that is that part that represents density dependence, it ends up being 0. So when you multiply that by the other part of the equation, the R times N, you end up with 0 population growth, okay? So hopefully that made sense. So you can see then that 1 minus N over K part that's circled in red on the screen, that's the part that is what's making it a density dependent response, right? It's what makes the population show that density dependent growth. Okay, so again, when you look at the graphic, you can see how that's working. At the start of the time period, when the population is small and growing, it initially grows in this very rapid fashion, right? We have this exponential growth. But as the population starts to get larger and closer to carrying capacity, then growth stops, okay? Because that 1 minus N over K value becomes 0, okay? So we can sort of see how that works in a mathematical way. Okay. And ecologists have been interested in identifying, where populations will grow at the fastest for various reasons, right? If you're trying to manage a population, you want to, maybe you want to harvest the population, but you want to maximize the growth rate of the population when you do it. So, one of the reasons we might be interested in knowing the population size where growth is maximized, again, because we might be interested in managing the population to produce the most new individuals, or maybe it's a game species, like a species that's hunted. So we want to make sure we maximize the individuals produced for issuing the hunting and fishing licenses. Maybe we're looking at an endangered species, and so we want to manage conditions so that the most individuals possible are produced. Okay, so there's lots of reasons why managers and biologists might want to know when is the population growing its fastest. And it turns out that the maximum rate of population growth is when the population is at half of its carrying capacity. So that's here. So this K over 2. So population growth rate is maximized at half of carrying capacity. K divided by 2, half of carrying capacity. And so we're going to consider 2 ways to look at this. There's 2 arguments to explain why population growth rate is maximized at half of carrying capacity. One is a verbal argument, the other is a mathematical argument. And the mathematical argument does actually have to do with calculus. And so we're going to do an actual for real bit of calculus today. But first, we're going to do the verbal argument just to sort of explain why this is happening. So again, we're going to look at why half of carrying capacity is when growth rate of the population is maximized. So again, from the verbal argument, when the population is, we're going to talk about it when the population is really small, when the population is really big, and what happens at that middle point. So starting with when the population is really small, the per capita growth rate, it's going to be close to the maximum, right? Because there's lots of resources for everybody, right? The population is small. So that little r value, the per capita growth rate, is going to be really high, okay? There's very little competition. So this means that per individual, that per capita growth rate per individual, the growth rate's really high, but there's very few individuals. So overall, the population is not going to grow very fast. Sure, you've got a couple individuals that are maximizing their reproductive output, but there's just a couple of individuals who are reproducing. So overall, the overall population size is not growing that quickly because there's just so few individuals to contribute to the new individuals in the next generation, right? So a small number of individuals only has the potential to produce as many, few individuals as they can because there's just few of them, right? So while the per capita growth rate is really high, maybe even close to that maximum, that RN value, the population growth overall is low because there's only a few individuals. Okay. Now, if we go to the other side and we look at when a population is approaching its carrying capacity, when we have a population that's really big, now there's lots of individuals there who could reproduce, but the competition is so intense because there's so many individuals that almost nobody is reaching its per capita growth rate, its maximum per capita growth rate, right? The per capita growth is really low because the competition is so intense. So since there's individuals present, but they're not reproducing many offspring because of the competition, again, the overall population growth rate will be low. So again, at small population sizes, overall population growth rate is low, even though a few individuals are there producing at their maximum, but it's just a few individuals. On the opposite end, when the population is really big, now you have lots of individuals there who could potentially reproduce, but the competition is so intense that they're not reproducing successfully. So again, we have a small population growth rate overall. Now, you go to the middle of the road, right? In a population that's halfway to its carrying capacity. Now, you've got enough individuals so that a significant amount of reproduction can happen. There's not too much competition, right? It's not overly crowded. So there's not a lot of negative impact of that intra-specific competition. So the per capita growth rate is high. And also, there's enough individuals to reproduce without competing too much. So as a result, the overall population growth rate is highest. Okay? So again, at this halfway to carrying capacity situation, now you've got high per capita growth rate, that little r value, and you've also got a lot of individuals who can successfully reproduce because the competition is not yet totally intense. So you have your highest growth rate for the population at half of carrying capacity. Okay, so that's the verbal argument for how that works. Now we're going to do some calculus for real. Okay, so if you, I don't know if you guys remember this, for those of you that have had calculus, I think everybody must have had calculus to be able to get into this course. If you want to find the maximum, to find out in an equation, if you want to, or a function, if you want to find out where the maximum is, if you remember, the way you do that is to take the derivative and then set it to 0. So that's like a calculus rule. So if you want to find out, the maximum growth rate, then you need to take the derivative with respect to n and set it to 0, right? So we're gonna do that. Okay, so starting with the equation, right? So we have dn over dt is equal to that rn n times 1 minus n. Okay, so we have the equation, right? So the first step if we want to get ready to take the derivative. It makes it a lot easier if you multiply it out. Okay, if you multiply it out, because it's a lot easier to take the derivative if you multiply it out, right? Because we've got this RMN factored out of the equation simplified. So we've got to multiply it back through. Okay, so now it's RMN, right, which is that 1 minus RMN squared, because we've got 2 n's now, over k. All right, so all I did here was factor it through, okay? Because it's a lot easier to take the derivative. Okay, so, and this is still dn over dt. So if you remember, we want to take the derivative with respect to n. And when we do that, it means that on this left-hand side of the equation, now we're just going to have n. That's the point, right? We're taking the derivative because we want to just get it to population size. We want to get it to that n value. Okay, so we're going to take the derivative with respect to n. So if you remember, I actually used to really love calculus, but maybe I'm weird that way. But if you remember how you used to take the derivative of something. So when you look at this equation, this n, this actually means n to the power of 1, right? And the way you take the derivative is you bring that 1 down and then there's no n's left over, so it goes away. But in this case, when we have n to the power of 2, if you remember, that means there's 2 n's here. So you can bring the 2 down and then there's still 1 n left over. Right? That's how we take the derivative. It's an abstract concept, but it also just basically requires memorization. But that's how it works. So if we take the derivative with respect to n, then we end up with n equals, right, Rm minus 2 Rm n. So that's the 2 that came down, and there's still that 1 n left over k. Right? So again, we took the derivative. So that the n that's here is gone because we used up that n when we took the derivative. But over on this side of the equation, we had 2 n's. So we bring the 2 down, and then we still have an n left over. That's just memorization back to how you used to do calculus in first year university. Okay. All right. So the next step, as I mentioned now, we want to find a maximum. And when we want to find a maximum with a calculus function, we set it to 0. Okay. So to find the max, we have to set it to 0. So that means that it's going to be now 0. I'm going to just erase it and do it this way because it's easier. So now we have 0 is equal to that function, right? Okay. So the next thing we're going to do is we're going to keep trying to simplify it some more. So now we're going to factor out that Rm again. Okay, we're going to bring that Rm out again. So now we have 0 is equal to Rm times 1 minus 2n over k. Right? All I did was factor out that Rm and simplify it that way. Okay? So again, now, right, when we want to find a maximum, we take the derivative with respect to n, and then we set the resulting equation to 0 to find that maximum. Because remember, we're trying to find where population growth rate is maximized. Okay? And then I simply factored out the Rm, and this is what we have. So now that we have that, if you look at what's on the right-hand side of the equation, one of these two factors, so we have Rm here, and then we have this other factor that's in the parentheses. That means those two things are multiplied by each other. The left-hand side of the equation is equal to 0. So that means that something over here has to be 0, right? 0, so either Rm is 0 or 1 minus 2n over k is 0, right? Because something times 0 is 0. So we know that something here has to equal 0. That's just simple math, right? So either Rm is 0 or 1 minus 2n over k is equal to 0 because it's an equation. It has to equal on both sides. All right, so if we think about this, right, again, we've got these two things that could possibly be 0. Either Rm is 0 or 1 minus 2n over k is 0. So if we first start with the Rm value, if you remember, Rm is the maximum per capita growth rate. If it was 0, that would mean that the population would have never started growing at all. It doesn't exist. I mean, ecologically, it doesn't even make sense, right? So it's not going to be this RM value. That can't be zero because it just biologically makes no sense. I mean, we are using this math to try and understand some biological principles, right? So the maximum per capita growth rate can't be zero because biologically that's just like a non-starter. It doesn't make any sense. So that means that it must be this piece of the equation that's equal to zero. It must be this 1 minus 2n over k part of the equation that's equal to zero, okay? So that's what we're going to work with. I'm going to go back over here. Okay, so what that means is the piece of the equation that must be equal to zero again, it must be this part, right? So I'm going to just write that over here. So 0 is equal to 1 minus 2n over k, right? Because we've said that this Rm value can't equal 0 because biologically it makes no sense to have a maximum per capita growth rate of 0. The population just couldn't even exist, okay? So it must mean that this is the part that is 0. So now I'm just going to work out this a little bit. So this is the same as saying 1 is equal to 2n over k, right? I'm just bringing the 1 to the other side. So 1 is equal to 2n over k. And then we're going to get rid of the k on the bottom on that side of the equation, right? So we multiply both sides by k. And when we do that, right, we get now k is equal to 2n, right? We just multiplied both sides of the equation. But what we're after is the population size at which growth rate is maximized. Population size is this n value. We want to isolate that n, right? That's the population size. That's what we want to know. At what population size is growth rate maximized? So to be able to do that, if we want to isolate the n, we just divide both sides by 2, right? Okay. So if we do that, you see that n equals k over 2. Right? And there's the formula that population growth rate, the size of the population at which growth rate is maximized is when k is over 2. Okay? So the maximum rate of population growth is at a population size that is half of carrying capacity. Right? So here, in this case, we did use some for real calculus. And so, just pointing out why they made you take calculus in first year is because it actually does apply to biological and ecological principles. And this is one of the ways it does. Again, we took the derivative with respect to n, and then we set it to 0 because when you set a function to 0, that's when you can find the maximum. And what we are exactly trying to find is the maximum population growth rate. And that happens when population size is at half of carrying capacity. So that's the calculus argument for why that's the case. Okay. All right. So we can now look at that in a sort of a picture. So this is how it looks. So now we've got population size on the x-axis, and we've got population growth rate on the y-axis, dn over dt. And so we have this moon sort of shaped curve, right? So at small population sizes, and at large population sizes, that growth rate is a low value. But at halfway to carrying capacity, it's the highest value. Population growth rate is the highest. Okay, so we've seen that the population growth rate depends on population size. If we can represent that by this graphic, so it shows that population growth rate, dn over dt, is the highest at halfway to carrying capacity. Okay. So population growth rate depends on that population size. Okay. So you should know how to explain this with the verbal argument and know how to show it with calculus too. Okay, so now at this point, I want to take a few minutes to compare how exponential and logistic growth look. We've made graphs of both of these growth models in using different axes. And so there's 3 sets of graphics that I want to go through here to show this comparison. So the first one, this is population size versus time. Okay, and so on the left we have the exponential, and on the right we have logistic. Okay, so again, this is over time, the x-axis is time, and the y is population size, what's happening to population size over time. So for the exponential, the population gets larger and larger and larger over time, right? Increase, increase, increase. But for the logistic, the population growth, the population initially gets bigger on an exponential sort of shape, but then eventually it hits carrying capacity, right? So the population initially grows rapidly, but then it slows and eventually stops growing once this carrying capacity, this population size of carrying capacity is reached. Okay, so you can see the comparison there of the different shapes of the curves that represent exponential and logistic growth. Now we can look at the comparison of dn over dt versus population size. So this is growth rate, right? The change in population size with respect to time, dn over dt on the y-axis, compared to population size, right? So for the exponential, right here on the left side, population growth rate increases as population size increases, right? We have a positive slope for this line, and this line, the slope of this line represents little r, the per capita growth rate. And again, remembering that in exponential growth, r is a single constant value. It does not change, right? So it's this value of the slope of this line, y equals mx plus b, represents the slope of that line, right? So the per capita growth rate is represented by this positive slope of the line. Again, a single value because it's constant. Birth rates and death rates are not changing in the exponential model. For the logistic, on the other hand, this is the graphic we looked at that's this sort of half moon shape instead. So population growth rate compared to population size. Population growth rate is maximized at half of carrying capacity. Population growth rate is lower at small population sizes. Population growth rate is low at high population sizes, and it eventually is zero when we get to carrying capacity, this K value, okay? So population growth rate is maximized at half of carrying capacity in the logistic model. And then finally, this is the dn over n dt, and if you remember, that's little r, right? That's the per capita growth rate, this dn over n dt versus population size, okay? So again, in exponential, the r value here, this dn over n dt, it's a flat line because again, it's a single value. In the exponential growth model, r is a single value. It does not change, right? So that's what's represented here. It's a flat line, okay? So the r value is a single value, so no matter what the population size is, it's that same r value, okay? So for exponential, r is just this straight flat line because the per capita growth rate isn't changing with population size, r is a constant. For the logistic, on the other hand, the r decreases as population size increases towards the carrying capacity. So it's a negative linear relationship. Remember that negative rise over run, that negative slope, negative Rm over K, all right? So in the logistic growth, we have this linear decreasing value, okay? So for logistic, the R decreases as population size increases towards that carrying capacity. So it's a negative linear relationship. And so logistic is a good general model of population growth. It fits for a lot of organisms, in our case, animals. It fits roughly, and we see it in quite a few different species. But there's ways to actually make the model even better, to consider how we can make it more accurate for some animals. And of course, you know, as I said before, when talking about models, if we make things a little bit more specific, then it's going to be less generalizable. We have that trade-off between accuracy and generality, right? But we're going to include the idea of time lags now into the logistic model. So a time lag happens when the population growth rate isn't responding immediately to the current environmental conditions. It's actually responding to conditions that already happened in the past, okay? So the time lag occurs when the population growth rate isn't responding immediately to the current environmental conditions. It's actually responding to things that happened in the past, that happened before the present time. So for example, the birth rate in a population depends on the population size when the individuals got pregnant. If there's a really long gestation period, so say there's like a 12-month or 18-month gestation period, when those individuals are actually born, the environmental conditions could be quite a bit different than back when the females first became pregnant, right? There's that time lag of that lengthy gestation period. So again, the birth rate in a population depends on the population size back when the individuals got pregnant, okay? And then there's this lengthy gestation period so that the growth that results from those pregnancies, it's going to happen, later than the environmental conditions of when everybody got pregnant, okay? So that's a kind of a time lag. And in that specific case, related to the length of gestation. And so for some animals, some mammals especially, right, that gestation period is really long. Another kind of lag is more focused on resources, okay? So a resource response to the population size. So for various reasons, the response of the resource, so we're talking about the resource being the thing that's responding, like maybe plant growth in response to herbivory. So it's the plant response that we're talking about. So the plant might not respond to the population size of the herbivore immediately. So the population of herbivores one year may determine how much plants will grow in the following year. So the food might be plentiful in the current year, but if the plants are damaged because of herbivory and they don't grow back, then food will be scarce the next year, right? So this is how the food resource is responding. Okay, so how do we model that into the logistic equation? We can add a time lag. It's represented by this Greek letter tau, which is, I have this sort of backwards JT thing here, but it's tau. And so this is how we incorporate it into the logistic model. So tau indicates the time it takes before the population growth rate responds to the population size, okay? So it's the amount of time it takes before the population growth rate is responding to the population size, okay? So the density-dependent part of the logistic growth equation is going to be related to the population size, tau time units before the present. So that's why we have this time minus tau, right? So it's going to be reflected in that time before the present. And that it's going to be based on how many units, and those units are the tau part of that equation, okay? So the density-dependent part of the logistic growth equation, that part that's in the parentheses there, it will be related to population size, tau time units before the present. So that NT minus tau part there in the equation represents population size, T time units before the present. Okay, so the formula for the logistic equation, the logistic growth, then we add this tau to that piece of the equation. So the result of a time lag is that the population, it's going to grow above carrying capacity since it's not going to respond immediately to being at carrying capacity, right? There's a time lag in that response. So the result is that the population is going to grow above K, grow above that carrying capacity, because it's not going to respond immediately to being at carrying capacity. So tau time units, after it reaches carrying capacity, then population growth will finally be zero and the population will start to come down again. It'll respond to finally being at K, but it'll be tau time units after, right? So after that, the growth is going to be negative and the population is going to start responding to being at K, and it's going to decline below carrying capacity, but then again, it's not going to respond right away to being below carrying capacity. So there'll be a delay before it starts to go up again. So you can see with the way I'm using my fingers, it leads to oscillations in population around carrying capacity. So again, the population is it's going to grow above carrying capacity before it realizes it's at carrying capacity. And then it's going to finally realize it and it's going to come back down, but then it's going to go below carrying capacity by tau time units before it realizes it's gone below carrying capacity. And I'm using it realizes. The population doesn't realize anything. It's just a way to say it to hopefully help it to be understandable. So a time lag is going to lead to oscillations around carrying capacity, okay? So there's a few ways that this can happen and how it can look. So the first one there on the top are these damped oscillations, okay? So this occurs if the population initially cycles around its carrying capacity, but the cycles become smaller and smaller, and eventually the population just sort of flattens out to stay at its K value. So initially, the time lag is changing, right? So in the stable limit cycles, this occurs when the population continues to oscillate in a regular sort of fashion, right? So you have the population going above carrying capacity here, and then it realizes it's gone above and it starts to decline, but then it even goes below carrying capacity, then it finally realizes it has gone below carrying capacity and starts to go up again. So you get this sort of stable limit cycles around fluctuations, these oscillations around that carrying capacity. The last one is this unstable oscillations. And so this one's a really problematic one. So if this occurs, if the population cycles become larger and larger, and typically it results in extinction. And the most common pattern is just to have what's shown here in the graphic, just one cycle. And you can see it looks a lot like the exponential version of the red deer example, for example, that we used as an example. So you have this initial grow, 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 get above carrying capacity, and then bam, crash. And that's it. It goes extinct. So there's only actually one cycle. So again, it looks sort of like the exponential. But this is when it just goes way far above carrying capacity. And by the time it responds, it's too late, and the population is gone. So the damped oscillations, they represent a fairly stable situation because eventually things come and sort of flatten out around carrying capacity. The stable limit cycles, it's not as viable as the damped oscillations because during stable limit cycles at the bottom of those curves, the population gets dangerously small. And you know that small populations are subject to extinction vortexes, right? We learned about that already. So whenever the population gets to this dip, things get really dangerous for that population. If the population can recover, okay, but this is a dangerous situation. And of course, as I said, for the unstable oscillations, these almost inevitably lead to extirpation or extinction. Okay, so we can consider some factors that are going to affect the stability of these oscillations. So in general, the farther away from carrying capacity, the farther above carrying capacity that the population grows, the more dangerous things are, right? The less stable the situation is going to be because the population just went way too high above carrying capacity. Those resources are so depleted, everybody is compromised, okay? So this is going to lead to this far crash below carrying capacity. So that's bad, right? So there's two factors in the model that affect how far above K a population might go. So again, the farther above K the population goes, the more problematic it is. And there's a couple of reasons why K might go K might go far above. So the first is the time lag. So this is why I brought up this time lag issue. So if the time lag is really long, right, if the tau value is really high, this results in populations growing for a longer period of time before they respond to being above K, right? So as a result, increases in that tau part, that time lag value, are going to cause populations to grow really far above K. And of course, that's going to decrease stability and make oscillations that are too big and lead to problems, maybe leading to those, the total crash, right? Okay. And also, if the RM value, if that maximum per capita growth rate value, if that value is at a really high rate, that means the population could also grow within a given time. If that RM value is really high, the population is going to grow larger and larger. So increased RM values can result in populations going much further above K. And so that's going to also decrease stability. Okay, so those two things, that a really long time lag and increases in the maximum per capita growth rate, mean that populations might grow larger than K, increasing that instability or decreasing stability. Okay, so we'll consider a couple of examples here for populations that cycle. So several species of small mammals, especially in northern areas, undergo these population cycles. So examples are some voles and some lemmings, which undergo 4 to 5 year cycles, right? There's a peak in these populations about every 4 to 5 years. Another one that you've heard about, of course, are snowshoe hares, which undergo 9 to 10 year cycles in population. And the snowshoe hare cycle was originally attributed to predation. It was originally attributed to the lynx, which are specialists on snowshoe hares. And there could be, of course, some that's going to definitely contribute to it. But both hares and lynx undergo population cycles. So they're both cycling. So they might not always be completely related to each other. So hares cycle even in areas where there are no lynx. So how do you explain that then? So again, some of the story is probably based on this predator-prey relationship. But the hares still go through these 9 or 10 year cycles, even when there's no lynx there. So how do you explain that? So it's not apparently predation that's causing the cycling. So one explanation might be the impact of the mammalian herbivores on the plants that they eat. So it might be, again, the resource that's driving that cycling. So it appears that herbivory decreases food quality, right? So there might be a lag in the return of the quality of that food resource after the mammal population declines. So the best quality food for voles and lemmings and such is really fresh new plant growth. And so the nutrient levels in the older plant growth are not as high. So at a vole or a lemming population peak, all the fresh new vegetation has been eaten, right? And so then after that, the population of mammals is going to start to come down because now the food resource is really low quality, right? And so then there's going to be a time lag until the new plant growth happens that's higher quality, and then the lemmings and the voles will follow that and increase in size again, eat all that fresh new growth that's highly nutritious, and then they'll start to decline again because now there's none of that good nutritious stuff, and then the plants will regrow. So you can see how this would lead to this cycling, right? The snowshoe hares also cause a decline in food quality of their resources when they're at peak numbers, because when they're eating, their herbivorous habits cause a production of toxins in the coniferous needles that they feed on, right? So there's a response in the plant to produce the toxins, which is then going to reduce the quality of food for the snowshoe hare, so then they'll decline in numbers. The plant will be like, hey, now I can be healthy again, and it'll stop producing those toxins. The snowshoe hares will then catch up, eat it, the plant will respond, right? And so you have these cycles, okay? And that's what's shown in the graphics here. I think that one thing is so ironic is that the population size for the grouse here is actually quantified by how many are shot, which just seems to be a bit counterintuitive, but there you go. That's how those data were collected. Okay. All right. So just a little bit of a summary slide here then of population growth. So the two main ones to learn about, to know about, are exponential and logistic. And again, the key assumption under exponential is that little r, per capita growth rate, is a constant value. The birth rates and the death rates are constant. They're not changing. And here's the equation that we developed for exponential growth. Population size at time t is equal to the initial population size times e, which is the base of the natural logarithm, to the power of the per capita growth rate times time, right? And so I posted on D2L some study questions for you to work through to use this calculation, and to also look at other things we talked about last lecture with respect to calculations, like doubling time and that kind of thing. So I also posted the answers on D2L, and I just posted the final answers. I didn't put all the steps on how to get there because I want you guys to solve that. That's how I want you to study for the midterm exam, is to work on those practice problems. And you'll know if you did them right because the answers are posted on D2L for you. All right, and then today we talked about logistic. Population growth was a bit more realistic because it's very unusual for populations to be able to grow indefinitely, right? So in logistic, this accounts for a density-dependent response. It accounts for the fact that as populations get bigger, resources become depleted and populations can't continue to grow forever. So here we have per capita growth rate decreasing as population size increases. And again, a bit more of a realistic scenario. It's density dependent. The density means it's dependent on the density of the population or the population size. So population growth rate, we also derived verbally and using calculus that population growth rate is maximized at half of the carrying capacity, right? So I want you to understand where that comes from. And then here's the equation that represents the logistic growth. So this is the change in the population size with respect to change in time is equal to the maximum per capita growth rate times population size. And then in the parentheses here, we have the density dependent part of the equation, which is 1 minus n over k, or k minus n over k, right? And keeping in mind, again, that this piece of the equation here, this r times n, this is the same thing as exponential. If you look back at the first couple of ways we talked about the exponential growth, right? This change in population size with respect to time is equal to population growth rate times population size under exponential. But now in logistic, we add this density dependent piece, and that's what makes that curve respond to population size, okay? That is population growth. I also posted some study questions for logistic on D2L as well, so you can see the kinds of things that I will ask on the exam related to logistic. And with that note, we do have the midterm exam next class. So it's on D2L. You have to know how to do life table calculations. You have to know how to solve these population growth problems, which is why I posted the examples on D2L to serve as study practice for you for that. So now I will stop sharing my screen and we can have a conversation about stuff related to the exam a little bit. We have a few minutes. I see that there is a chat here, so I'll just go to that. Let's see. Is that equation true for all cases where you'd want to know the maximum growth rate? What do you mean by that, Cameron? Is that true? Is it generally applicable across all animals? If you want, you can turn your mic on, Cameron, if you want to ask that.
Well, I had, Kel, can you hear me?
I can hear you, yeah.
Okay. I asked that question when you were doing the, showing how where the equation comes from on the chalkboard.
Yep.
So like, if we were ever trying to find in like a certain ecological case, like we're trying to find the maximum growth rate, would we always use that n equals k over 2 equation, or would there be like, does it differ from case to case?
No, so it's a theoretical construct, right? So theoretically, it should apply to all the animal populations that we might try to model.
Okay, thank you.
Yeah, and part of that is because that carrying capacity is going to be specific to the population we're talking about, right? So if we're talking about small mammals that live in a certain reach of parkland or something, we're going to know what the carrying capacity is of that region of parkland that they're living in, right? And we're going to know what the population size is, kind of thing. So it's already sort of accounting for whatever differences in life history and patch quality and things are there. So theoretically, it should apply. Are there any other questions? So I noted at the start, I'm not sure if everybody was here at that point, that I have asked some questions to the biology technologists about how to get respondus onto your computer when you're going to be writing the midterm. So I'm hoping what will happen is that Melanie Smith, Dr. Melanie Smith, who's one of the biology technologists who helped me do the exam for animal histology at the end of the year last year, that she'll be able to give me just a very straightforward, here's the instructions on how it works, and I'll put that on D2L, so it'll be there. But I do think you have to download respondus right when you start the exam. I think that's how it works. For people that have, for those of you that took animal histology with me last year, do you remember how it worked? And again, I said at the start too, because I'm on a different end of D2L when I'm in there, I don't know what it looks like for you guys to try to do that. I know some of you were in histology last year. Do you remember how it worked?
I had to use it for organic chem or biochem, and I did it for that before this class. So it automatically just had it ready for your class when we did it last year. So I think once you start your first exam, if you haven't downloaded it, it should prompt you to do it. It should download it, and then you're ready to go, I think.
Yeah, that was my understanding too. Thanks, Awab. That it lets you like open the test. The first thing you're going to have to do is download respondus, and then it's there. Amy says, last year we had a link and we installed it a day before the test. Oh, okay. Oh, but then Carol Ann says there is a link that will appear when we start the midterm. Yeah. So yeah, I kind of remember both of those scenarios too. So I want the main thing, right? So the Jordan asks a really important question here. Does the download take time out of the test completion time? And I don't think so, but keep in mind that I have given you enough time. You will definitely have enough time to do the test. So if it takes half a minute to download respondus, it should be totally fine. Yeah, so Amy says it didn't take very long. So it should be totally great. So that one of the things that I want you to try to do as best you can is make sure you have a good internet connection wherever you're writing the test. If you can be hardwired in instead of wireless, like if you have an Ethernet opportunity to attach to your modem, that maybe for the test you might want to do that rather than, you have a modem somewhere in your house and you probably have wireless, all over the place, but you'll have a better connection if you go down to where the modem is and you actually do a hardwired connection, if that's possible, just to be safe. But the main thing I want to say is don't panic. So we'll work it out. You know, I understand that not everybody's got great internet connections, and it's just so weird to be doing a test in this online way. So if you run into trouble, you can send me an email, and you can also, I put this in the, I put this on D2L. Tom Fenske's extension is 2278. And if you dial that extension, it goes right to his cell phone. And so he's also going to be on standby. So both Tom and I will be on standby as you're writing the test. At the very end of your exam, I have to go to a really important departmental meeting that I can't miss. So for the last 5 minutes of the test, I won't be there, but Tom Fenske will still be there. I have to go to a meeting at 11:15, and the test goes till 11:20. For those of you that don't have accommodation, for those of you with accommodation, of course, it'll keep going, and Tom Fenske will be available. So you can email either Tom or I if you run into trouble, or you can call Tom's cell phone at extension 2278, and then he can contact me, and I can leave. I've already told the department that I have a test running that day, and if I need to leave the meeting, I'm going to need to leave the meeting. But I was not able to. Actually, the meeting's really important. It's a meeting of a review of our undergraduate program. So they want me there as a professor teaching in the undergraduate program. The external reviewers of our program want to talk to me. So of course, it's important to be there. Okay, it won't be a Dropbox right yet. Download does not affect the timer. It will force you to download before being able to start it. I'm pretty sure. Yeah, that's what I thought too. I thought it would not detract from the time. It shouldn't detract from it. So the midterm exam will open up, and then and the quizzes part. And so right now the exam is not opened. It's not viewable for you guys, but I will open it so it's viewable, and then you'll be able to click into it, and you'll be able to download Respondus, and then on you go with the test. Are there any other questions? Once you start the exam, is it times or will it finish at 11:20? The exam will, I have set it up so that the exam is at the length of time, not the exact time. So it won't stop at 11:20. It'll stop at exactly, what is it, an hour and 20 minutes. So it's going to stop after an hour and 20 minutes. Yeah. And the timer starts after you activate lockdown. It's good. I mean, some of you have experience with it, so I appreciate your actually answering the questions for your colleagues in the class too, to help us all understand how it works. Carol Ann, you've been using tests on D2L since first year, really? Wow.
Yeah, with Dr. Lamotte.
Okay.
He uses that a lot, so.
Right. Okay. Well, then if that is it, you are free to go, and I will see you all in a couple hours for the lab at 1 o'clock.
Thanks, Jackie.
You're welcome.
Thank you very much. See you soon.